Also, I mentioned that you would choose to sign in for a teacher, and we'll start passing the support around, and then it'll be in the back.
Well, thanks very much for coming and for what may be your interest in this. So I have a couple things to talk about. One of them is I'll talk about the research that we do at Cornell in designing and building spacecraft. And it is a research topic. I mean, it's one of these fundamental questions that still isn't really well answered. What are the best ways to build these things, design these things? So it's very much a research problem. But then I also have something else to convince you of by the end of this. So if you stick around for the end, I will see if I'm successful at that. First, spacecraft are the things that orbit the Earth or go beyond the Earth. We don't refer to rockets as spacecraft, that's something else. But I think you also understand that right now, the only way to get something into space is to put it on a rocket. So first step is put your spacecraft on a rocket. Next step is the rocket drops it off somewhere in space. Now, people ask the question all the time, why does the satellite stay up there orbiting around the Earth without falling back down again? And it's kind of a simple thing. It's going so fast that its own centripetal acceleration pulls it away from the Earth, like swinging a rock over your head on a string. So I'm not going to go into those physics very much, but the nice thing about having a satellite, the thing to keep in mind is once you got it up there, as hard as that is, it stays there pretty much forever. Unless a few other things cause problems. One of those things would be atmospheric drag. Even a few hundred miles above the surface of the Earth, there is still enough of an atmosphere that it drags satellites down gradually. So I'm going to tell you a story about how to build your own spacecraft. This is a thing. Turns out, even people your age build spacecraft these days and launch them. There was a high school in Virginia, Thomas Jefferson High School. About 2 years ago, they built a small satellite called a CubeSat. I built a small satellite that can send text messages from space. I mean, it's not a huge technological achievement, but what's awesome is these are people that are 15, 16, 17 years old doing this. What has changed in the last, let's say, 10 or 20 years is the availability of electronics, computers, and all sorts of tools that allow you to build your own spacecraft. And I'm not kidding about that. It is possible for you to spend a few hundred, maybe a few $1,000s, if you have that kind of money, and put together the components of a satellite, and then NASA, or actually some other companies, will now launch those for free. So the bar to entry into space is really low now. And it's an exciting time for all of us interested in this question of how do we build our own spacecraft? How do we, what future do we see in space? It's exciting to think about the fact that we might not see the kind of future that our fathers and grandmothers anticipated back in the 60s. It might not be great big spacecraft, great big colonies on the moon. It might be thousands, even millions of individual robotic explorers or private space missions. That might be the future. So who's heard of a company called SpaceX? Yeah, so a certain number of you. So SpaceX, does anyone want to say what SpaceX is? What they do? So it's a private company building rockets. Unlike a lot of companies whose stated purpose is to maximize shareholder value, one of their objectives is to settle the planet Mars, which sounds kind of crazy, right? But I'm telling you, these days, that is not so far out as you might think. The man who runs that company, Elon Musk, he's one of the many internet billionaires who've turned their fortunes towards space. There are actually quite a few of them. I'll talk about a few of them here in this talk. But because of the rise of consumer electronics, and again, how easy it is to build some of these things, now it's possible for a startup company focused on space technology to make a profit. So for the first time in history, we're seeing small companies pop up, not just to do computers or maybe some kind of manufacturing out of plastics, but small companies popping up to do things like asteroid mining, sending small spacecraft around the Earth to take pictures of it. Or there's even a company in Ithaca here called Ursa Space. Ursa Space is building very small radar satellites to look at the surface of the Earth and track shipping containers and look for all sorts of important science information. All that is possible now because of how relatively simple it's become to build your own spacecraft. So I'm going to try to tell that story. In the context of SpaceX, let me mention something called the Falcon Heavy while I pass around these little bits of swag here. So go take one and pass it on. These are little bookmarks from NASA, so thank you, NASA. These are pictures of the Space Launch System, NASA's new very large rocket. When this is finished, it'll be the biggest rocket ever. It will be able to launch something like 100 metric tons into space, and at a cost of about $2 billion per launch. It's kind of a lot of money. SpaceX has this other rocket called the Falcon Heavy. Hasn't launched yet, but it will soon. Falcon Heavy is almost as capable as the SLS rocket, and it costs about $150 million to launch. So what is that as a fraction? Something like a 15th or a 16th or something, the cost? That can change the world, because the price of launching a spacecraft into orbit is kind of a lot. Even now, the cheapest you can do this, launching a huge spacecraft on a big rocket, benefiting from the economies of scale, it's something like $1,000 per pound to launch something into space. Now, I'm going to tell you a story about these little satellites. It's actually even more per pound to launch these into space, but if we make them small enough, the total cost is so low that actually you and I could afford them. So let's talk about that. Here's a distinction I want to make here. The research we do at Cornell, Cornell is known for a wide range of research. Some focuses on science, some focuses on technology. I'm in the technology part of the world. So I think it's helpful to understand when you're going into some discipline that involves math or science or engineering, understand which kind of thing you are. Are you an inventor or a discoverer? I think if we talk about science, science is very much the practice of discovering, right? Finding out what hasn't been known before, interrogating nature, doing experiments to tease out the truth of things. Engineering or technology is about building something new, coming up with ways in which we can design something that's never been designed before. So in a way it's discovery, but really it's more about creation. It's about innovation. So depending on what appeals to you most, think about what could be a good major for you if you're thinking of going into something kind of scientific. The reason I bring that up is this picture right here. So this is a picture of the most recent Mars rover from NASA, built by the Jet Propulsion Lab in California. Anybody know what the name of this rover is? I think I heard Curiosity. Right, the Curiosity rover, formerly named the Mars Science Lab. What you see up there is one of the very first pictures that the Mars Science Lab or Curiosity rover took. It's black and white because that's a so-called thumbnail. They have beautiful full-color pictures, but the technology that we have to send that data all the way from Mars, the communications technology, isn't powerful enough to send just continuous streams of full-color pictures. Instead, we get a few black and white or grayscale thumbnails. Someone in a mission operations center in California clicks on them and then downloads the full-scale, 12 megabyte, whatever it is, color picture. Well, this is one of those thumbnails, and it was just used to sort of verify that the cameras were working. You see that little picture up here in the middle? It's a kind of little, kind of an icon-looking thing. It looks a little bit like the Curiosity rover. The original plan that the Jet Propulsion Lab had was to put its logo, JPL, right there. Now, NASA, being the government agency that it is, said, no, it's not a JPL project. This is a NASA project. It's a nationwide endeavor. So we'd rather put the NASA logo there, and they fought back and forth about this. And they finally agreed to disagree, and nobody got their logo in this very first picture from Mars. But the JPL engineers took a different route. This rover has 6 wheels on it. It's a very sophisticated mechanical system with something like 37 joints. It's quite subtle. Every one of these wheels has little holes and spokes in it. In the wheels, there are holes for the dust to come out of, right? But those holes are cut in a very specific pattern. As the wheels travel over the surface of Mars, you can see up there, they make an imprint that spells out in Morse code the letters J, P, L. So actually, the JPL engineers won this battle because every time the rover takes a picture, it's taking a picture of JPL all the time. It's kind of a secret little Easter egg, I guess you could say, in the operation of the rover. But you could also see it as the JPL gang sort of tagging the surface of Mars with their gang sign, the JPL gang sign. What this communicates to me is not just that engineers are clever, but actually they take very personally the idea that they are sending something of themselves into space. They have a really close identity to those things that they've created here. So they wanted to personalize it, and you can understand that, I think. I think particularly if you are the inventor type, the creator type, it occurs to you that you want to put something of yourself out into space or in the form of a car or computer software or whatever it might be. So there are thousands, millions of people interested in space. This is a picture taken during the second to last space shuttle launch. STS-134 it was called. Something like 750,000 people descended on southern Florida for that particular launch. For the very final space shuttle launch, 1.5 million people went to Florida to see that. They were camping out in the streets and in hotel parking lots. I take that as evidence that people around the world, certainly within the nation here, would like to be in space, would like to participate and engage. And that's actually what this talk is about. Citizen space is the term that we use for how individuals, it doesn't have to be citizens of a specific country, but individual people can in fact go to space. This is a picture of a CubeSat. It is in fact a cube shape, but that's not what's important. What's important is it's a standard. It's kind of like JPEG or MP4 or something like this, right? Something everybody agrees should be compatible with other things. So the CubeSat standard is a specific shape, 10 by 10 by 10 centimeters. It's 1 kilogram of mass, and therefore it's 1 liter of spacecraft, if you know what I mean by the units of measure there. So it's 1 liter of spacecraft, and the components that you would put in there are largely available off the shelf. You can go online and buy these things. So you can actually assemble your spacecraft, or if you want, build it from scratch. But in any case, you can build it out of existing commercial components. I think that is, again, what I'm talking about, lowering the bar to entry into space. Since we can do that now, since any of you could actually do this, all that stands in your way is how do you get this thing into space? Now, I also tipped my hand earlier. I said that NASA will launch these things for free. That's true. There's a thing called the CubeSat Launch Initiative. Any educational institution, including a high school, can apply to ILANA, it's the name of the program, Educational Launch of Nanosatellites, can apply to this program, and if you're accepted, and it's about a 50% acceptance rate, then you get to launch your spacecraft for free. They say there's no such thing as a free lunch or launch, but yeah.
How do you get accepted? Like, what are the things that they...
It's a great question. The criteria are you have to be well, two things. They look for the fact that you're going to be ready when the time comes. They want you to be able to assure them that your spacecraft will be finished in time for the launch. They're also looking for a degree of technical credibility. So when you say we're going to build this thing and we know what we're doing, they want to be able to believe you. But as I said, other high school teams have already done this.
But is it that, it's like that small?
Yep, that's it, that big.
And how
Size of a grapefruit.
to make one?
I beg your pardon?
Like, does it take a long time?
It kind of takes as long as you want it to take. I mean, if you have a lot of money, and we're talking about, let's say, $30,000, you could buy all the parts, put it together successfully over the course of a couple of months. But if you're designing these things from scratch, and let me tell you, that's what I'm interested in. I like the idea of creating something no one's done before. Then it might take you a lot longer because you got to figure all this stuff out.
What kind of functionality is in the CubeSat that's sent up into space?
That's a wonderful question. If you didn't hear, the question was, what kind of functionality is in these CubeSats? They look really useless, right? Like a little toy or something. Several things. From the science perspective, some of the things that CubeSats have done, they have demonstrated biological processes. There was something called GeneSat, another one called PharmaSat, that did some microgravity experiments involving bacteria and viruses and medicines. There's been actually a lot of success in measuring the ionosphere, which is this sphere of plasma that surrounds the Earth in the Earth's magnetic field. A lot of those missions, probably 15 or 20 of those missions so far. There have been very inexpensive and quick technology demonstrations, because one of the ironies for space is they say it can't fly until it flies. You really have to test it before you trust it. Unfortunately, the only way to really trust it is to test it in space, and if it can't fly until it's tested, how do you do that? Well, this is actually the answer. These platforms are so inexpensive that you might as well dedicate one to trying out a technology. If it only costs maybe $100,000. I know it's a lot of money, but in a NASA context, that's not that much. Only $100,000 to try one of these things out. That could save you millions or even billions if a mission fails. So there's a motivation for looking at these small spacecraft. Anyway, there's lots of science possible, and actually where they're going now, and this is something we're working on at Cornell, interplanetary CubeSats. There's a competition for building the first CubeSat that goes around the moon, and my research group is working on that right now, so if I have time, I'll tell you more about that. The way these launched, so this little 1U it's called 1 unit of CubeSat. That launches in a pod there with a total of 3. You pack them in there, it's spring-loaded, and then they all pop out together. Here's a video showing that. If you missed it, we'll see it again. There it goes. This is actually on the International Space Station where there's a CubeSat deployer. So let's look in the lower right. There they are popping out. It's kind of interesting irony that the largest spacecraft ever, the International Space Station, 400,000 kilograms, huge, huge spacecraft, size of a football field. that is now used to launch the smallest spacecraft ever. 1/400,000th of the size of the spacecraft. Anyway, this works well, and this is the free launch you get out of NASA if you want it. A message to tell you is that the number of these small spacecraft has increased a lot over the last few years. Just in 2012 to 2014, the number has almost doubled roughly every single year. And that doubling is similar to what's known as Moore's Law for electronics. Has anyone heard of Moore's Law for computers before? Can someone explain what that is? Yeah. The idea is that over time, the capability of processors and computers is increasing. In fact, it doubles roughly every 18 months, and yet the price is also dropping. So there's been this exponential increase in computer capability, which is why you can carry around a smartphone now and have in your hand more power than was ever used on the Apollo spacecraft. Anyway, same logic is going on here. There seems to be a Moore's Law for spacecraft. It could be that in a decade from now, there are not just thousands, but maybe hundreds of thousands of spacecraft coming from the Earth, representing a move by our species into space. Kind of a crazy tinfoil hat wearing idea, but I'm telling you, this is the trend we see. All right. In making your own spacecraft, you don't have to use the NASA Trident II process, which would, let's say, allow you to make a solar panel the size of a napkin that would cost on the order of $100,000. No, not at all. What we do at Cornell, we have this grill here. We get a piece of printed circuit board material. We take these triangular solar cells and place them on the grill and melt them into place. And that's it. And it costs about $50 for one of our solar panels. And they have never failed. So this approach is also not unique to us, but this is one way that you can build these things for almost no money compared to typical spacecraft. Now, the solar cells themselves are a funny shape. They're a triangle shape. That's because they are cut off of the corners of the much, much more expensive large solar cells used for things like geostationary commercial satellites or other military satellites. So we get the rejects, and in the process, we save a huge amount of money. So that's one thing that you can do to make things cheap. Here's another interesting idea. This is partly about communications, but also about innovation. So you know that in order to talk to a satellite, you probably have to use a radio. And these days, so who's heard of ham radio before? Heard of this? Okay. This is kind of like an amateur radio technology, right? It's been around for a really long time. In fact, the very first small satellites that launched right after Sputnik were amateur satellites of about this size, one called Oscar. And they've been continuing to do Oscars ever since, this ham radio community. So even though most of these guys are in their 80s, maybe 90s, there's been sort of a rejuvenation of ham radio because these amateur frequency bands that have stayed reserved for amateur use are now available for all of us to use for spacecraft. So all of these little tiny spacecraft are now communicating on these radio bands that have been around for 50 or 60 years. It's kind of a fascinating reuse of this particular part of the spectrum. Anyway, what's going on with this spacecraft, this is from a Japanese university, the Fukuoka Institute of Technology. It's called FitSat. FitSat is just genius. It does almost nothing except soaks up power from the sun, and then every now and then blinks out a Morse code signal from space with some super bright LEDs. So that sounds wacky. Seems like, how could you possibly see that from that far away? Well, you've probably messed with LEDs, right? You've probably seen how bright these things can be for almost no power. It puts about 200 watts worth of power into these LEDs, and in fact, they're bright enough that you can pick them up with a naked eye from the ground. Now, if you really do this right, you could get a telescope that pans across the sky and reads that Morse code. This one doesn't say JPL, actually I don't know what it says. But this is a completely new concept in how to communicate from space. Think of how democratic this is. All you need is your eyes, and you can get data from space. Now, of course, you want to record it in a computer or something else, but this is the kind of innovation that's possible if we throw away the last few decades of very expensive government-funded spacecraft engineering and ask, what could we do ourselves? Yeah? Yeah, so the FitSat, as far as I know, so the question was, does the spectrum of the light influence how visible it is? I mean, roughly, that was the question, right?
No, it's like, can then you have like more satellites in this spectrum before they
Ah.
before we can't communicate with that
Okay, so yeah, so you're talking about the ham radio frequencies?
compared to radio.
Right. Well, okay, so there's a lot to say about that. The question was, what about the frequency spectrum and how many satellites can you really fit in there? There are a couple of international organizations and one in the US, the FCC, that coordinates all these frequencies. And if you were to build your own satellite, you'd have to coordinate with them, but it's relatively easy. Send some emails, you submit some forms, it's not that hard. So you can coordinate the frequencies. But when I say a band, that band is really wide. For example, the so-called 70 centimeter band, when all of our spacecraft are in that particular band, they specify the frequency to 6 significant figures. So actually that gives you 1 million options, even within 1 megahertz worth of bandwidth. And there's many, many, many megahertz. So that's not seen as a problem yet. It could happen someday if you really have millions of them. But if I have time, I will tell you how we actually get around that as well. So I was really impressed by this mission because it's so innovative. You're just flashing lights, and yet you figured out a way, these folks figured out a way to communicate from space without using a radio. PhoneSat is another innovative one. So I might have been harsh on NASA a second ago, but I will tell you that NASA also has a lot of innovative ideas about these small satellites. One of them is something called PhoneSat. So as the name suggests, it is quite literally the guts out of an Android phone. So has anyone ever taken apart one of these phones and seen what's inside of them? There's almost nothing in here, right? It's like all screen and a battery and a little tiny electronics board. And yet that electronics board is enough for communications. It's typically got a gyroscope on it, so you know how it's pointed, and know how it's moving. Clearly it has power. It's got all the processing you could ever want. Basically, all of the components you would want in a spacecraft are already in a smartphone. So NASA tried to answer the question, could we in fact use all these very sophisticated consumer electronics and put them into a satellite? So they used the CubeSat as the platform for that. And to save time and effort, they didn't even bother with solar panels. They just put a bunch of big batteries in there and let it go. And the answer is yes. It turns out that these days, the electronics that are in your own smartphones or in your electronics that you've used every day are at least as good and probably better than the space-qualified electronics that NASA and others use for space. They don't do the same things, but they survive longer and they're built to higher standards, which is just fascinating. So in fact, we've gotten to the point where it's not like the space age is the leading technology. It's actually stuff like consumer electronics that's now driving how we explore space. Which also means they're much more accessible. I can go online and buy a little GPS receiver the size of your thumbnail for about $2 or $3. Compare that to the most sophisticated space GPS receiver. It's about 3 kilograms, it's about this big, it costs about $2 million. It's kind of ridiculous. So that's why these are becoming more and more popular. The PhoneSat people, 3 or 4 years ago, were successful in launching that PhoneSat. Oh, by the way, another cool thing they did was they actually had a website to send commands. So they actually had used the internet to communicate with it. Rather than building ground stations and all the kind of hoopla you would imagine for space, they just logged in and texted the satellite back and forth. Anyway, those guys created a company called Planet Labs. Planet Labs is a startup in San Francisco. It's been around for about 30 months now. They've got something like $100 million in private venture capital funding what they're doing. They are making small satellites that observe the Earth. You know, Google Maps, right, uses some satellite imagery. What if you had Google Maps type imagery that was updated once an hour? That means you could track wildlife with it, a lot of science applications there. You could watch during the course of a day how crops are performing, so you could decide how to fertilize them or water them. You can track your shipping containers, maybe for reasons of national security or just watching your property. Keep an eye on your backyard to see if the neighbor's kids are playing in there that you don't want them to. Whatever the reason is, this could enable completely new applications for data from space. So here's a little video from those guys. This is basically a CubeSat, although it's tripled in size. It's a so-called 3U CubeSat. So triple up the 1U size, you get this 3U CubeSat. It also has deployable solar panels, which is important to give it more power. But they only weigh about as much as, you know, a laptop, a little bit less. Also, the Planet Labs people are able to fabricate one every 6 hours. You know, a typical military satellite takes maybe 10 to 15 years to fully design and build and complete. 6 hours is a complete game changer. It totally changes the conversation. Not only is it cheaper to build these things because they're so fast, but also they can afford to make enough of them to cover the Earth the way that's shown in that diagram there. So in the future, you might have an animated version of Google Maps thanks to Planet Labs. A number of my students are now working at Planet Labs. I'm sure they have internships if you guys are curious, so you could look into that. A little bit about spacecraft scale. So I've made the assertion that small scale is helpful because it's inexpensive. Up until a few years ago, the most commonly launched type of spacecraft were these, the dotted red line up there in the middle, or virtually all of the Department of Defense and NASA and other satellites. They were huge, the size of a car or a bus, until about 2012. And then, suddenly, maybe not suddenly, but clearly in 2012, the most commonly launched type of spacecraft became these little tiny things. Now that does not represent getting out of the business of space. It's exactly the opposite. It's businesses getting into space. It's individuals getting into space. So CubeSats are roughly that 1 kilogram size. What we're doing at Cornell is research in maybe what's the next generation. So here's potentially the next generation of this. Here's another satellite. A little hard to see this. It's about 3.5 centimeters on a side. It's got solar cells on each side. Has a little antenna coming out of the top here. You can come check it out afterwards if you like. It has a processor on here that's actually used for car key fobs. You press the button to open your car. All the processing power we need and all the radio capability we need is already on that chip. So that's all that we need to make this a fully functional satellite. There's a lot of cool things this does, and I can tell you more about it, but we built 100 of these things, and we launched them in 2014 on a mission called KickSat because it was funded by Kickstarter. Has anyone heard of Kickstarter before? Yeah, so someone tell us what Kickstarter is? Yes, go ahead. Yeah, exactly. So you can ask the public for help. In the case of KickSat, we asked the public for $30,000. If a backer provided enough money, we would actually, that backer program one of these spacecraft. So in many ways, these aren't much different from Sputnik, which launched in 1957. It just beeped as it went overhead. But this is like a Sputnik for the 21st century. It uses modern components, and it is so inexpensive, it's about $30 worth of parts. So even though on a per kilogram basis, that's ridiculously expensive, the point is, I can now put something into space. I can do real science with these things, and I can do it for $30. And again, that further changes the conversation. So we call these sprites. One sprite is 4 grams worth of spacecraft mass. That's the second dot to the right. Eventually, we're thinking we might get rid of the circuit board material and a lot of the metal and plastic and have only little slivers of silicon flying in space. There are many really interesting ideas what we could do with that. One of the ones that you might like if you're a science fiction nerd, like I am, is we could accelerate those really fast. There's all sorts of ways to get things going really quickly, different kinds of guns and particle accelerators and all sorts of fancy stuff. If we do that and get these things up to maybe 1/10 of the speed of light, which is not completely out of the question, we could send one of these things to the nearest star in about 40 years. So within our lifetimes, we might be able to put a sensor in another star system. And that's one of the objectives for these really small spacecraft. Absolutely. If you didn't hear the question was, wouldn't they be destroyed by stuff flying around in space? Yes, I totally agree. So what are some examples of things that could destroy these?
Like stuff, asteroids, and stuff that's fallen off of
Space debris, all that. And aliens that are malevolent and have really good eyesight, yes. Any other ideas? Yeah, so particles, right. I agree. What was that? Exoplanets, if it happens to strike one, sure. I mean, I'll tell you that one of the main issues you would encounter is radiation. Galactic cosmic rays are very high energy particles whizzing around from all sorts of different sources in the galaxy. In fact, if you ever are fortunate enough to go into space yourself, if you close your eyes, you'll see little white, bright sparks. Those are galactic cosmic rays entering your skull, striking your optic nerve, and causing a little bit of damage at the molecular level. And every time it zaps part of your brain or your nervous tissue, you see a white spark. So astronauts who fall asleep have to think about that as they're relaxing. The fact that there are these high-energy particles drilling holes for their brain at all times. Now, in fact, you may remember that one of the very first communications from John Glenn, who was the first American to orbit the Earth, not the first human, by the way, was that he saw stars that seemed to be following his spacecraft. And since then, people have thought that was UFOs or other crazy explanations. No, it was just his own optic nerve being damaged by galactic cosmic rays. So yes, those could definitely drill some holes in the sky. The answer to your concern, or the way to address the concern is, remember how cheap these are. I could launch about 1 million of these things on one rocket launch. So let's say there's only a 1 in 100,000 chance that this thing actually makes it all the way to Alpha Centauri or someplace. That's still 10 I've got, right? So in fact, the way to engineer reliability into something like this is maybe not by making it absolutely perfect and protecting it perfectly, but instead just launch a whole lot and hope or know that a certain fraction are going to survive. It's a very different philosophy, but it's what's opened up now that commercial electronics are so inexpensive. All right, so moving along here. This was the result of the Kickstarter campaign. My student, Zach Manchester, started this thing. He has a neat video, which I will show you. And he asked for $30,000. We got almost $80,000, which is enough for 2 spacecraft. So we're launching the second one in March of this coming year. I will show you his video later if you're particularly confused. So I've said everything I need to say about this, and you can come up and check out the actual hardware. Here's a video from that was meant to be the mission. I'll tell you what happened in the mission. Here's our 3U CubeSat deploying these 100 or so individual sprites. That is exactly how it would happen mechanically, by the way, and I'll show you a video proving that. It should have worked great. His design was excellent. It worked exactly as intended. At the last minute, NASA said, you know what, we don't like you deploying these things, so we want to change the rules. Our plan was to deploy them half an hour after the launch. Instead, they say you have to wait 30 days. So, okay, we're going to be good soldiers here. We will change the spacecraft. Zach actually flew to the launch site. They got the spacecraft out of the pod where it's supposed to launch. He reprogrammed the timer to be 30 days, not 30 minutes. 16 days, not 30 days, 16 days. And put it back in the spacecraft. It launched, and it worked perfectly, except here's what happened. It was only meant to survive half an hour. It survived a long time. Oh, a test, right? This is our kind of ghetto test of all this stuff. We have cardboard boxes and video cameras and bubble wrap, but you know what? It worked fine, so we're happy with it. Here is Zach putting it into the pod that's supposed to launch it. It's just loaded like a, I don't know what, a spring-loaded thing. That's all it takes. The other cool thing that Zach had innovated here was for these little tiny sprites to communicate to the ground, all you need is a laptop and a handheld antenna. So it's, other than the laptop, it's about $50 worth of hardware. And that's all it takes to communicate to these little tiny spacecraft over 1,000 kilometers away. So, again, props to him for doing such a great job designing this thing, but it's a kind of innovation that you wouldn't have seen if it hadn't been for the rise of commercial electronics. Also, all of his hardware and software designs are online. So if you've ever used GitHub before, you can log on there, pull out his code, and actually make it. We've had people come up to us at conferences and show us the sprites that they have made, and we're hoping this becomes a kind of open source platform like the CubeSats. Anyway, here's the mission. So it launched April 18th, 2014 on that SpaceX rocket. The Dragon capsule deployed it, and the timer started at 16 days, counting down towards 0, at which point it would deploy all these little sprites. So it's hanging out there, hanging out. Finally, 12 days later, there was a radiation anomaly, a 1 in 50 years strong solar storm, a so-called coronal mass ejection, sent high-energy particles toward the Earth. Also, at the same time, the spacecraft happened to be flying over part of the Atlantic Ocean called the South Atlantic Anomaly, where there's lots of radiation. So it got kind of a double zap of radiation, and that caused the flight computer to reset. But thanks to Zach's design, the fault protection on board handled that, started up the computer again, and reinitialized what was going to be a 30-minute timer. But remember, NASA made us change it to 16 days. So now, even though it was only 4 days away from deploying, the timer reset to 16 days again. So we're waiting 16 days, and the thing was not going to last more than 30 days anyway, because of drag. Remember I mentioned at the beginning, the atmosphere is up there just a little bit, but enough to drag that back into the Earth over the course of a month. With 2 days left on the timer, May 14th, the spacecraft re-entered without deploying its little spacecraft. So we were all very sad. So was the public. This actually had garnered a lot of attention in the media, at least if you follow things in Wired and Slashdot and so forth. It was all over that. But we're trying again. So if we're successful, maybe you'll hear about it then. I already mentioned we're going to head toward putting everything on one chip for various science fiction reasons. One of those reasons might be planetary exploration. So here's a picture of a familiar planet, which is what? Mars, yes. Mars has been the attention of the planetary science community for several decades now, ever since Viking landed in about 1976. For the almost 40 years since then, we've been sending rover after rover, and there's been a number of spacecraft orbiting Mars as well. It's been a great campaign looking for evidence of past life on Mars. Seems pretty clear to most of us that it's a big dead rock at the moment, but maybe it harbored life in the past. There are questions we could ask about this, though, that are very difficult to answer with a single rover. It might be hard to find evidence of life in one exact place. But what if we could put 1 million sensors all over the surface of Mars? If there's only a 1 in a million chance of finding that evidence of life through a particular chemical test, maybe this is the way to do it. So we'll see what happens. But it's not just about little satellites. Some people who are building their own spacecraft also have in mind sending humans there. For example, the Mars One company.
Mars One will establish human settlement on Mars in 2023. In that year, the first group of 4 humans will land on Mars. Only 2 years after that, another group will join the settlement.
Or so they hope. I mean, that would be great if that works. These things all take money. You know, these little tiny spacecraft that I've been talking about, they're inexpensive because they're small. But it's very hard to send small humans to Mars. You know, if you can come up with a way of shrinking people, then yeah, let me know. But for right now, without the Willy Wonka technology, we cannot do these sorts of things. So instead, the plan is, once again, commercial hardware. And what is the other feature, if any of you have been following this, what's the other feature of the Mars One mission that makes it different from the way NASA might do this? Yes? It's a one-way trip, exactly right. You know, the fact is, because of the rocket equation and some other things, it is way cheaper to send people there once as colonists than to send them there and then bring them back as tourists. I mean, it's on the order of a factor of 20 to 50 times cheaper. It's really remarkable. It maybe costs $5 to $10 billion for one of these Mars missions, which is a lot of money. But compare that to the maybe $50 to $100 billion for the NASA version. Now, NASA's committed to that path, and I think it'll be successful when it happens. But those of us like me who are impatient and ready to retire to Mars, we're not necessarily ready to wait for that. Once you're on Mars, though, maybe there's some things you could do. If you're Matt Damon and you run out of potatoes and you can't get back to Earth or you're super hungry, what else could you do? I like the idea, by the way, of The Martian. You know, it's an example of creativity, problem solving, out of necessity. If I were in a position to be on Mars as a one-way trip, I think one of the first things I would do is to try to construct the spacecraft that would take me back home. You know, this is like being on Gilligan's Island or something and building a raft. I think that would occur to almost everybody when you're shipwrecked. Maybe, okay, the movie Castaway with Tom Hanks, okay, not Gilligan's Island. But anyway, this is the design that some students at Cornell worked on. It uses water as the propellant. Now, you might have heard there's water all over Mars. In fact, about a meter below the surface, there are some places on Mars where it's mostly water. It's almost like it's one big skating rink in certain parts of the planet, just covered up with some dust. So there's water as much as you could possibly want. We didn't know this maybe even 5 years ago. In fact, just recently, I think you saw the announcement, NASA scientists discovered flowing water on Mars. It's kind of filthy stuff, full of nasty chemicals, but still basically flowing water. So we got the water. How do we use it for propulsion? Here's a map of that, by the way. Here's the water by weight in the upper Martian surface. Clearly near the poles, it is something like half or a third water. But even in the driest parts of Mars, it's a few percent water already. And a few percent's pretty good. I mean, that's just like Earth, essentially. So you can pull water out of the Mars environment. We also know that this water is here because of meteor impacts. Here's a picture of where a meteor struck the surface of Mars, and all that white stuff, that ejecta from the crater, is actually water ice. So we came back a few months later with the same spacecraft, same crater. That ice is gone. It's not like someone took it, which would be interesting, but no, in fact, it just sublimated or evaporated into space. So it's all there. At Cornell, we've been building one of these. This is a rocket engine that runs on water. So you fill it up with water. You use electric power, for example, from the sun, to separate the water into its hydrogen and oxygen molecules, and I think you all know about that, or you haven't been taking chemistry. So you get a hydrogen-oxygen gas mixture. We ignite that with a spark plug in the upper right there, and then propulsion happens, right? That explodes, it goes out through the rocket nozzle, and you can see a picture on the right of a test showing that that's exactly what happens. So all we need is water and sunlight, which, if you think about it, is kind of what anybody or anything needs for life on Earth. Maybe it's going to turn out that surviving in space, or a sustained human presence in space, uses exactly what we always knew we needed on Earth: clean water and sunlight. You have a question? Well, so for propulsion, you need to throw something out the back of the spacecraft, right? So let's say I'm a spacecraft. If I want to go that way, I've got to throw some mass that way. So if you're using, your question was, what about, can we use electricity directly? Well, typically you would have to accelerate something using the electricity. One thing I guess you could use would be electrons themselves. Problem is, if you start shooting electrons out very quickly, the spacecraft charges up electrically, and those electrons you shoot out come right back at you again. So you can't just use electrons, but maybe you could accelerate something else. Did you have something else in mind? So for example, there's ion propulsion, so-called. You could use, let's see, xenon gas or plastic, or almost anything. And you could accelerate that stuff using electromagnetic fields. You absolutely could do that. You're right. Because it is cheap and easy. It is so inexpensive, in fact, so universal, that if you take off from Mars, maybe you don't make it all the way back to Earth, maybe you land on an asteroid or land on the moon, you can refuel there as well. But it's very hard to find, xenon or PTFE or mercury or whatever it is that you want to use in an ion propulsion engine. So the electric propulsion is a great idea if you have a very finite use for it, but it's not a great idea if you're trying to create a sustained means of traveling around the solar system. But water is so pervasive that that is probably the right fuel. In fact, we could look at asteroids and the moon as our gas stations. There was an engineer named Kraft Ehrenke years ago who said, if God had meant humans to travel in space, he would have given us a moon. It's pretty much the ideal place to launch exploration of the solar system from. And that's what we're talking about here. So we've built one of these electrolysis propulsion engines. We're putting it in a strangely shaped CubeSat. That's going to be our means of orbiting the moon and ideally winning the contest to be the first spacecraft to orbit the moon. So we will see if that works, because there's water everywhere. Now, some of the students at Cornell do this sort of stuff as well. There's a microgravity aircraft at NASA that flies these parabolic trajectories. You sit in the aircraft, you feel 0 G for about a half a minute or so, and you perform experiments. Here's some people testing out a 3D printer for space. Now, why would we want this? Well, what if we get to the moon and, yeah, we want to get our water for fuel, but what if we want other things too? A habitat, maybe a shovel to dig up our potatoes, whatever those things are, and we didn't think to bring one with us. But we have all this matter. In fact, you could say that all the mass we need to explore the solar system and settle it permanently is already up in space. It's just in the wrong shape. So a 3D printer addresses that problem. Could we 3D print our way into a sustained exploration paradigm? I think the answer is yes, and this is one of NASA's strategies for long-term exploration. And it starts with experiments like this. So if you were an engineer at Cornell, you might have the chance to fly in a microgravity aircraft and try out a 3D printer in 0 G. In the longer term, maybe it's something like this. This is an idea from Southern California, University of Southern California. It's called contour crafting. You take a little water and some secret sauce, and then you make cement out of the dust on the surface of the moon or asteroids or Mars. And that's actually a lot easier than 3D printing, right? You're just sort of mixing up a stew of this rocky material and printing it out into landing pads, runways, habitats, very, very large telescopes. There's a lot you could do if only you had cement on the moon. And some of us call that massless exploration. This is kind of a science fiction idea from one of the asteroid mining companies called Deep Space Industries. Their notion is start with an asteroid, You have some kind of device, don't know what it is, that sucks the mass out and turns it into a space station, or turns it into more mining equipment, or maybe prints more 3D printers. There's enough ideas out there that it's a very rich research area. Yes?
What do they mine when they mine it?
It's a great question. Some people think that the right thing to mine is water. I think in the near term, that is sort of not the case, because NASA or no other company really has plans to base their exploration on water. Not yet, maybe eventually. Instead, most of them want to mine platinum group metals. These are things like literally platinum, but also heavy metals that we're actually running out of on Earth. I don't know if you've heard of this, but the iridium material that you use in cell phones, we've only got about an 8-year supply left here on Earth. So very soon, we will be using different technologies for a lot of the antennas in our high-performance radio transmitters, because we're running out of this particular material. It turns out that most of these heavy metals on Earth come from space to begin with. They came on asteroids, which we call meteors or meteorites. So if you can mine the meteorites on the Earth, you'll find these materials, but we figured that out already. We know where they all are, or were. But I can tell you where a whole lot more are, and that's in space. So that's one reason why they might mine these things in space. Yes?
So if they have if they're thinking about having the asteroid mining technology, does that also mean they have the technology to recycle the stuff they can't use anymore that they've already mined?
Yes, I think that's the idea. So recycling, if you didn't hear it, could we recycle this stuff? Absolutely. In fact, even in the short term, one of the things that NASA might do is recycle waste from the International Space Station. The plastic bags from the food, and yes, astronaut poop, all that stuff. It's matter we spent $1,000 per pound getting up into space, that inherently it's got some value, if only we can reshape it into something else. Poop sat or something, I don't know. But yes, that's absolutely an interesting solution. All right, now as crazy as all this sounds, I'm telling you, this is the result of rigorous research at Cornell and other places. It is part of NASA's longer-term strategy. Those of you who believe mistakenly that NASA's out of business, that's not true. There is a plan for the future. Arthur C. Clarke, the science fiction writer, said it pretty well. He said, every revolutionary idea seems to evoke 3 stages of reaction. First, it's completely impossible. Then, it's possible, but it's not worth doing. And then, I said it was a good idea all along. That's roughly where we are right now. Right now, people are starting to recognize it's possible for millions of us to explore space, millions of us to use the resources in space for permanent settlement of the solar system. Let me leave you with this. This is what I'm going to try to convince you of. There's a Museum of Science Fiction in Washington, D.C. If you haven't gone, you should totally go. They have been working with Cornell and some other universities to create a CubeSat competition. It is open only to high school students. The opportunity here is to propose a CubeSat that's inspired by a concept from science fiction. The successful proposals, and there will be 8 winners, the successful proposals not only will get recognized with an award at a special event in Washington, D.C., so you can go there and get a nice trophy or something, but also the winning proposals will be built as actual, no-kidding spacecraft by these 8 universities all over the country, and Cornell is one of them. Now, I'm one of the judges in this competition, so I can't give you tons of help, but if you at Ithaca High School would like to create a team, I'm not going to stand in your way. Furthermore, you would be able to work with us at Cornell University to build this science fiction inspired CubeSat. Now, what do I mean by science fiction inspired? There's rules you can look at online. If you didn't see the website, it's museumofsciencefiction.org/CubeSat. I mean ideas that until you figure it out were just the stuff of science fiction. How about, okay, you know this idea in science fiction that if we're sending someone on a long journey, let's say from Earth to Jupiter, that we might want to put them to sleep. Sometimes they call that suspended animation or some kind of cryogenic sleep or something like this, right? Well, I'm not asking you to put a person on board a CubeSat and freeze them. But there is some science that can be done that has never been done before about how we could preserve life that way. I'll give you the example of these little creatures called tardigrades. Has anyone heard of tardigrades or water bears? Yeah? Okay, so can someone tell us about what these things are? What are these things? Yeah, maybe? Uh-huh. Yeah. Yeah, they're super small and they're everywhere and they're almost related to no other creatures on Earth. And they are really robust. They can survive intense radiation. You can dry them out and reconstitute them and they just spring back and do their little water bear swimming around thing. Exactly, they can survive extremely cold temperatures, to the point where we would wonder, well, maybe there's lessons learned here. There's something about their biochemistry that could tell us in the future if we wanted to freeze people or help them survive the rigors of space. There are lessons to be learned there. And maybe this even has benefits for us here on Earth, addressing problems of cancer or limited lifespan and other things here. So maybe the science fiction CubeSat example is we're going to do a cryo-sleep experiment. We're going to do a suspended animation experiment. You launch your CubeSat with some tardigrades in it. You have some kind of a sensor, maybe a camera. You freeze them for a while. You wake them back up. You take measurements, and you conclude something useful from that experiment. That's inspired by science fiction, but it's not itself science fiction. Here's another one of my favorites. How about antimatter propulsion? Okay, so if you've been paying attention to things like Star Trek, you know that antimatter is a way of storing energy in a sense, right? In an antimatter-matter collision, you get a huge burst of gamma rays. It's a lot of energy. It's like a nuclear event, right? It's exactly that. It's nuclear energy. But it's the most compact way of storing energy for propulsion we can think of that even agrees with physics these days. Could you make an antimatter-propelled spacecraft? I think the answer is actually yes. Maybe it wouldn't go very far, but you can buy medical antimatter, that is isotopes, online. You could collide those positrons with electrons that come from a battery. You can produce a little bit of that high-energy effluent. Maybe you heat up some water or something else, but you could demonstrate the basic principle of taking antimatter energy and turning it into propulsion. And again, you're not going to go very far with that using technology we think we understand. Still, it'd be the first time anybody has used antimatter for space propulsion. And I'm telling you that this is feasible at the scale of what US high school students could conceive of, if you're particularly interested and motivated to do this. So in the competition, the rules are, it's got to be a 1U CubeSat, so the 10 by 10 by 10 CubeSat. The price for building all the stuff, all the components, $10,000 or less. But we're not asking you to build it. We're not even asking you to do a lot of detailed engineering. You do what you can, but it's only like a 20-page document, and I think they're asking you for a short video that explains your idea as well. The deadline for the applications is early February. However, I believe we're going to change that to early April, so there'll be several months. In fact, most of the spring semester, you could actually be working on this particular proposal. You submit the proposal to the Museum of Science Fiction. A board of judges, including some cool science fiction authors, of which I'm not one, but there are many involved, will judge those entries. And then the winners, like I said, get a trophy, and someone builds your spacecraft. Most of the universities involved also will have summer programs where the winning team's students can go to their university and learn how to build spacecraft there. We're going to do that at Cornell. I can't speak for the rest, but we'll probably separate the winners up regionally. So if there's a high school close to Cornell, I can think of one, you have a good chance of working at the Cornell spacecraft labs to make this thing. So does that sound interesting to anybody? Yeah? Good. I hope it's at least interesting to some of you. There's no limit on the team size, so one person, I guess, could submit, or you could submit many from one school. That would not be a bad thing either. I'm glad to answer questions about this, but I don't want to keep you too long, so I think we're close to the hour. And I will stop there and take other questions if you have them. Thanks for your interest. So any other questions?
What's the most difficult problem now we face in space?
Let's see, question was, what's the most difficult problem now that we're facing in space? So from a technology perspective, I will say that if you're talking about a Mars mission, the hardest problem to solve is entry onto the surface of Mars. Right now, the estimate is we have to land very large vehicles on the surface of Mars, maybe 20 to 40 metric tons at once, in order for the people in there to survive the landing. That's difficult. In fact, the largest thing we've ever landed is 1 metric ton. So we need to increase our capability by 20 to 40. We have some ideas, but that's going to take a long time to fix. Thanks, a good question. Yes?
So you mentioned sending like a whole lot of very small friends to Mars, sort of for like scientific reasons, but from a more engineering perspective, has there been any research on like sending like there's a like little like ball of like stuff, I'll call it a catalyst, and it will use what it finds in Mars to essentially build something on Mars much bigger.
That's a cool idea. So the question, if you didn't hear it, was what if we could use something like these sprites and land them on the surface of Mars and they carry some kind of catalyst with them to build something even bigger. I mean, one answer to your question was, the answer is, has there been research on that? Not to my knowledge. Arthur C. Clarke had a science fiction novel called The Songs of Distant Earth, in which he speculates you can't actually send people very far, but maybe you could send their DNA, and then you need to sort of print them up somehow when you get there, and then teach them how to be humans again. And that's completely speculative, but could you use it as a kind of seed crystal? Could you use it to build other, larger pieces of rock around it and build bricks? And maybe. Carbon's a good example. So I think the answer is no, research has not really been done on that. I think it's a great idea. I think you should think about it.
If we cannot send that much stuff, why we in one? But why can we just separate into like 20 times?
Well, it has to do with how big people are, right? So, first of all, they're not going to send the fat guys to space, but they might send you. And when they send you, you come in a quantum of human, right? There's sort of a minimum size. Let's say it's, 50 to 100 kilograms in general is the size of a person. Well, for that person to survive the landing, you need a certain amount of structure. You need a certain amount of oxygen and water and guidance and control computers and propulsion and all that stuff that makes the spacecraft actually work. And it looks like for one person, it's on the order of maybe 5 to 10 metric tons. But you don't want to just send one person because you need a crew to make it work. So even a 2 to 3 person crew, as small as that would be, that's like the Apollo size, it's still 20 to 40 metric tons when you add everything up. I mean, that seems disappointing, but that is roughly the estimate. Now, maybe there's some radical ways in which it could be different, but that's the current plan.
But why we just send like 1 or 2 person and with a group of robotics which will solve the problem?
Well, right now the plan is to send a lot of robots early on to create food and find water and make a safe environment. That's already planned, but even with that, it looks like you need, let's think about a car, okay? So a car is about 1 metric ton, give or take, right? And so 1 metric ton for a car keeps one person safe, maybe 4 people safe. But traveling the surface of Mars is so much harder than having just one car. I'm going to say it's 20 to 40 times harder. So that's kind of your answer, right? I mean, that's what it takes to drive a car down the road, is 1 metric ton. To drive something, so to speak, into the planet Mars, 20 to 40 times more mass. And I will believe that there are other ways to do it, but right now that's NASA's best estimate.
I mean, if we need that kind of much stuff to keep people like alive, food, water, or air, why we don't just throw them out in space? Like a part you said we need to throw out to accelerate in the space.
Yes, well, so what lands on the surface of Mars is the bare minimum to let them survive the landing, and probably a day or 2 worth of food. That's all. Before that lands, you will already have sent landers with water and food for the long duration mission. So it's not like it's 1,000 kilograms of mass and 19,000 kilograms of food. It's hardly anything else. It's the bare minimum necessary for landing and then survival for a day or 2. Everything else will already be on the surface of Mars, ideally. Well, anyway, thanks a lot for your questions. It's great to chat with you. I'll be up here if you want to talk some more. Thanks.